Okay, this is a video talking about transistors and FETs and relays. We have a device which uses a Micrologic 1000 PLC. This PLC has two relay outputs and has two FET outputs. A FET is a field effect transistor. This is what a transistor would look like from, some of you would say, the old days, and this was in the old days. Transistor has three little pins on it. It's used to pass electricity, electrical current. Here we have a diagram of a simplified transistor. The idea being, there's a piece of solid-state silicone with some doping of another compound in there. You have a voltage applied across the silicone through a resistor to a negative. But this doping acts like a switch, but it leaks a little bit. So when you apply voltage, you always get a little bit of current flow. Even on these FETs, you can get some current flow, which can cause other problems not being discussed in this video. But back on the transistor, you have the cathode, the anode, and the base. By adjusting the voltage of the base, I in essence can let more current flow through the transistor. This is solid state. When this is being used to drive a valve directly, which even if it's beefed up to be a FET versus a transistor, which is a high power transistor made to carry high current loads, over time this junction wears out. It just eventually wears out. We have a customer who has one of these controllers. The air valve is always on when the power is applied. This means that this piece here has shorted out, so it's just passing current all the time. So when the power is applied to the PLC, whoosh, the valve turns on. It's always on. This is where the start-stop command comes in from the PLC logic. It's not working for this customer. This chart here shows, I don't think the detail will be clear, this shows variable current as a function of the voltage applied here for this particular transistor from this old circuit board. There. So what do? We began selling this product line assuming we'll be using low power valves for the air, half-watt valves. These FETs would be fine for that. We ended up using regular 24 VDC 10-watt valves. These FETs will eventually burn out. Again, the burnout is when that junction right there just wears out due to electric flow. It just burns out. But it burns closed, not open. It burns closed in this case. This is a relay. It's a mechanical relay. You energize the coil. There are little pins in here, switches that can open and close. This is what's in the first two outputs over here. So solvent valves have a relay output in them. The air valves have a transistor output in them. When we first began selling these and saw people using 10-watt valves, we knew there was a problem coming. There's a relay right there from Allen Bradley that we can connect to the PLC and isolate the FET output from the valve. This thing here is like this, but it's packaged very differently. One odd thing about this is you may recall I mentioned there's always a leakage current flowing through here. If this base voltage is pulled all the way down, which if it's designed a certain way means there should be no electricity flow, there's always a leakage current through a transistor. This relay here, I can take this transistor, I can turn it on, it'll pull the relay in. When I turn the transistor off, the leakage current is enough to keep the relay pulled in. Therefore, sometimes the relay won't drop out. We get around that by putting on a biasing resistor, shown here, which draws off the leakage current from the transistor. So FET outputs are transistor outputs. Transistor outputs are solid state junctions. They're not mechanical relays. They're solid state. They can age, they can wear out, they can be overloaded, they can be burned. In industrial process control, you don't want to use a FET output unless you're driving another transistor. Having a FET output drive a regular valve, 10-watt valve, is a mistake. So we have isolation capacity on this. We have a number of customers who got these in the field before we realized the phenomena. And we had a call recently saying, a customer says, hey, when I turn the power on to this air valve output is always on. The air valve's always on. This happens to be in our simplex line. So before you push the touch panel on the simplex to start the station, the air valve is on. Well, that's no good. The problem is that internally, inside here, this transistor that's inside that controller is broken. It's burned out, non-repairable. Only option, replace the PLC. In this case, this PLC is not EEPROM programmable. This MicroLogic 1000 can only be shipped from here, Newton, Mass, programmed to the customer. They then have to make sure they're using a relay like this with a biasing resistor on both these two outputs. That's air station 1, air station 2. That's solvent station 1, solvent station 2. Typically we want to have PLC control systems with relay outputs, not FET outputs. So this is a story about a transistor, which I can say, as an older person, in 1971 at UNH in Durham, New Hampshire, I made a transistor, actually doping the silicone and actually doing a raw transistor design in a chemical engineering lab. So I date myself in this video. Hereby signing off, saying have a great time with FET outputs. Don't use them. Isolate, isolate, isolate. Thank you. Goodbye.